This recording or video will show, we'll talk about the natural growth model and the logistic growth model. The natural growth model is a model that we've seen showing up in a lot of nature, and that's why it's called the natural growth model. And it involves the number E. E doesn't look like a number, it looks like a letter, but it actually is the number 2.7171828, and it keeps going on forever and ever and ever. It's like pi, it's an irrational number that never ever stops. It just shows up in nature. It's named E because um, there was a mathematician named Euler that actually kind of proposed it, and it's been named after him since then. So that's where it came from. And it looks a lot like the exponential growth model because it is exponential growth. It's just instead of having a base of 1 plus r, the base is this number e. The e does appear on your calculator. You'll find it, there's an e to the x button on your calculator, and there's also just an e button on your calculator. But do realize that it's an irrational number that never ever stops, never repeats. It just goes on. It's kind of like pi. So this is the growth model, and in this model, just as always with all models, P of t is the population size in t time periods, whatever time period you want to go with, whatever you want to find that. P0 is your initial population at whatever time you decide to call your time 0. T is your just number of time periods, and K is known as your growth rate. So this is how fast something's growing. It's not exactly the same as R, but it kind of relates to this idea of the growth rate. And then E, again, is this number that goes on forever. Don't try to write it, just write it as E. We're going to spend more time with E in later chapters, later material, but I just wanted to kind of see what this model looks like. A lot of people use exponential growth, and especially half-life, they use the base E. Physicists love base E, and they do a lot of work with that. But you also see biologists use E instead of using the 1 plus R growth exponential problem that we were working with before. So the other one is a logistic growth model. So a linear growth model kind of looks like a line. That's what linear means, is a line. And it just looks like a line. It just keeps going up and up and up, and it just slowly keeps getting up higher and higher. An exponential growth model, again, starts at your P0. Both of them start at P0. But this one kind of starts off slow and then suddenly just picks up and goes really, really fast. And in fact, it will surpass the linear growth model very relatively soon. And the exponential growth model and the natural growth model look exactly the same. And we see a lot of biologists using this model, this exponential, or especially the natural growth model, for describing how populations grow. But it turns out that it doesn't really grow exactly like this. It does at the start. When a population is starting, it grows kind of like this. But at some point, it's going to start slowing down. And when we started seeing that happen with populations growing, they start kind of slowing down. We realize that there's a different model altogether. And that model is this one here, called the logistic growth model. So it starts off kind of looking like an exponential, goes fast, and then starts to level off. And the reason it starts to level off is it gets to what we call the carrying capacity. As the populations start growing, especially if you think about like a bacteria growing in a dish, at some point that bacteria is going to grow out of its space or grow out of food. And so at some point, it's not going to have enough space or food to keep growing. And so it starts to level off at what we call the carrying capacity. Every natural environment that we see has this thing called a carrying capacity. The earth has a carrying capacity. Even petri dishes have a carrying capacity. Most things we see have a logistic growth model. Most of what we see, though, is at this time period here, because this is really in the long run that it starts to do this. So that's why we can model a lot of things with the exponential growth model, because at the start, they are probably growing like this. It's not till many, 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 many time periods that it might start to do this. So we're going to kind of look at what this logistic growth model looks like. The model doesn't look like anything you've ever seen. It certainly does not look like the exponential growth model or the linear growth model that you've seen in the past. This model has this thing called m in the top in the numerator, and this kind of exponential growth model in the bottom, but not really because it's actually negative, but it's in the bottom, so that makes it growing. Some weird things happen. Notice it does involve this number e and not the other rates that you've seen in the past. Again, as always, P of t is your population size and t time periods, whatever you want that time period to be. T is your number of time periods, whether it's years, months, days. This m is a very important thing. It's what we call the carrying capacity. And I'm going to go back up to the graph for just a second. If you happen to have a population that grows so fast at the start that it goes above the carrying capacity, it will start to come back down, which means it's going to have some dying off happen until it gets closer to this carrying capacity. So you will see every growth model we've ever seen will kind of level off at this growth carrying capacity. And this carrying capacity is known as a horizontal asymptote. You can cross it at the start possibly, but you will come back down to it until you kind of go along this asymptote. Horizontal asymptote is just a line you can never ever cross. Well, I shouldn't say never ever cross. It's actually a line that you head towards as time goes farther and farther and farther and farther along. So as you get farther out here, you're going to get closer and closer, but you're never going to actually touch it later. You can cross it at the beginning, though. You just won't. You get closer and closer and closer to it as you get farther along. And that m, that numerator, represents that carrying capacity. K and C, this K here and this C here, are just some positive constants that come about in the model. We are not going to actually in this class look at how do we find K, C, and M. We're going to just look at how do we use if we have this model already set up for us. Classes that actually worked at that are more advanced than what we want to get into, but it is possible to find K, C, and M in situations and come up with these models, but we're just going to give you the models in this class. So let's take an example. Let's say I give you the model. So my model for whatever we're having to grow here and whatever was involved in this problem as 85,240 over 1 plus 0.6 e to the negative 0.15 t. My initial population would be, as always, it's the population at time 0. It's wherever we want to start, and we're going to call that time 0. So if we put 0 in here, into this formula, we can actually calculate what this would be. And it's going to be putting 0 into it. Remember, 0 times anything is 0, and anything to the 0 power is 1. So it's actually going to be 1 plus 0.6 in the denominator, because e to the 0 is actually the number 1. And then you got 85,240 in the top. Divide that, and that actually tells you how many starting. So let's say this is the number of students that are at a university. I believe this is Arizona State University's population, and this is how many students were starting at this from whatever time it was, and we were starting in 2009. So there were 53,275 students in 2009 at ASU. And let's say we want to find out how many students are going to be there in 5 years. So you can put 5 into this formula, and it works just the same. Again, your calculator will be equipped with this E button. You can go and plug it in, and you'll find out that in 5 years from 2009, which is 2014, there were 66,416 students. If we said in 20 years from 2009, which would be 2029, then the guess is it's going to be 82,768 students. Now, as a reminder, this is not necessarily what exactly it will be. Things can change. Things could happen to where more students want to go there and the growth actually changes faster. Or it could be that something happens and students don't go there. And so this is what we predict it to be. It doesn't necessarily mean that's what it actually will be. Now, let's say I want to find the carrying capacity. So going back to this formula, looking at here, this number right here in the numerator, I can't copy it, not copy it, but I can't highlight it very well. But this number in the numerator is your carrying capacity. So if this is the number of students at ASU, this is how many students at the moment ASU can actually accommodate. And so if you want to find the carrying capacity, then you just take the numerator, and that is how many students you can actually um, have that school. So ASU can only handle 85,240 students overall. Um, it may actually change at some point in the future, but that's what the value is right now. And that's how logistic growth models work.